and which makes your SOC very comfortably implementable. So that's why once you go for a large capacity of design or large components to be included in a SOC, we need to look at the hierarchical design as well as with a design reuse. The third factors, so which is normally makes more challenge on an SOC, is with respect to an physical properties. So the physical properties, so which will be makes us, so with respect to the interconnects. The second one is with respect to a design values or a process element values. So the interconnects, as we spoken, the interconnects, how it will be more delayed factor. So the delayed factor is also considered with the signal strength. The signal strengths normally occurs are the reduced due to a crosstalk, IR drop, ground bounds or a power ground bounds, etc., etc., etc. So all these factors which will be said as a single and as a signal integrity. So that is the major physical property we need to look at on for an interconnect for an SOCs. The second one is the design integrity. So you have n number of process elements. We need to make that to be presented as a single functional elemental values or single processed SOC component values. So while making a interconnect between these process elements, so we have so many factors which will be makes into a presence. So some of the factors which is influences our physical parameters to make my functionality reduction is an electron migration, hot electrons, wide self-heating, etc., etc., etc. So these design challenges, what you listed out, these are some of the design challenges I'm quoting here, because I'm majorly working on the NOC, network on chip. So I'm looking on, so with respect to that, how it can be made available to my design. So that's why I looked at on the timing closure, the large capacity, and the physical properties of that. So so look at on the how these challenges will be presented from year to year, and how your chip will be taken more number of gate by solving these challenges. So normally it is a linear appearance. So at the 1990s, it will be very small number of gates and a small number of chips. So at around 2000, it is increased very linearly. So now we have an exponentiality. So from 2002 and 2005, we had a more linear graph, compressed linear values. So at from 2005 to and today, so we got an exponential values. So the gates per chips is exponentially increasing by introducing more number of transistor in a single area or single micron values or micron area values. So that's what we come across with an 3G, 3G to a 2G, 2G to and 3G, 3G to and a 4G, 4G to and a 5G, 5G to and a 6G. So these mobile communication made us to introduce more and more number of gates into the chips. That's why, so we had, nowadays we have so many transistors, so many gates, which is goes within a single chip areas. So if I take the functional appearance of these gates, so inside the chip with respect to an hour, so it is more stagnant values, so more linearly stagnant values. So maybe nowadays it will becomes more linear, because as you are introducing more and more gates over there, so that the functionality of the gates is should be increased, so that we are the exponentiality itself will be makes the gates per hour to be presented so linearly. So the difference between the gates per chip to an a gates per hour will be defined as an a design productivity gap. So normally we need to make it this gap to be an a very minimum, very less, so that all the functionality which is defined at these gates to be available for your chips, to be available. So that's a major area how you can reduce. And today also we have some productivity gap. So we are trying to fill it out. So that productivity gap with the extra functionality which is needs to be considered. So the second major area which will be looks with this design productive gap with an a the presented to an a market. So we have very major factors which says us to go and reduce your areas or the shrinking all your design cycles. So for an a chip to be or SoC to be appearable. So there is a major factors which will be seeks there. So I'm taking the olden days data and I'm presenting here. So the military application is the huge demand at the 1980s. So but 1990s it will be becomes a very less. So similarly, the consumer electrons today will take our consumer SoC will take a major increasation. So than the military side. And industrial will be settled set on a middleware, so or midland, so where it will be taken from military to a consumer. So in the consumer, majorly the healthcare consumer industry. So nowadays will be booming like anything, and which will be consuming more SoC components over there. So that's why we'll come across with the device technology to be changed for this medical consumer electronics, and we are going with a quantum from a mass to an a quantum to an a spin to an nowadays we are looking at an memory in computing. So that is the evaluations which should be taken here. Today we are concentrating on how the memory will be take set inside the processor and or how the processor end will be presented at an a memory. So and it will be executed very fastly, so are very frequently and consuming all the functionality parameters. So that is a major end. So the medical electronics or medical SoC design so will be takes care of on the consumer end. So that is the major inclination over there. So if we are taking the consumerizations with an accelerations, so the consumerations in the 1980s very less, 1990 it's very huge uh, to be presented. So nowadays it will be occupies all your 360 uh, parameters, and so the rest will be very less and the consumer will be very more. So that's what I told. So the consumer so will be very more at that. So in that consumer, the 60 to 70% see is only with an a medical consumer electronics or medical and consumer parameters. Other things will be an very less. So in before this, from maybe from 2005 to an a 2020, so the major consumer will be an a mobile SoC design. So nowadays the mobile SoC design will be shifting from 2018 or sorry 2017 or 16 uh, to and today. Today it's making SoC to be a very occupation. So in these areas, the rest will be very less, very minimum. If I say that, so what the factors which makes your uh, consumer to be occupies more and more area. So with respect to a time to market, so it is with respect to the component which is presented for an SoC. So the SoC has been, as I think you are gone through that, the SoC may takes the CPU as a major factor. Not today, not only one CPU, you can have multiple CPUs over there. A configuration of the memories, different memories, the configuration of a different peripherals, memory connectivity, USBs, etc., etc., etc. So the different applications appearances. So maybe an voice codec, maybe an video frame analysis, uh, wireless link controllers, maybe an a Bluetooth wireless link controller, etc., etc., etc. So creating your synchronicity at the single end, that is the PLL, timers, etc., etc., etc. All these things will be presented for our cases at a single one, that is in a test cases. Some of them may be a digital blocks, some of them may be an analog blocks, Some of them may be an mixed block like an PLL, ADC, DAC, all are your analog and mixed signal blocks. Those are all the IPs which is already there, and you are taking care of those things over here. So what you looks for this multiple design disciplines? So you need to have majorly on digital hardware, which consumes more space on your SOCs or more appearance of your SOCs. So the second one, once you created a hardware, we need to have some controlling softwares. So that is, you are calling it as an embedded software. So maybe your middleware, maybe your uh, higher level parameters, etc., can be presented to take care of that. The third one, so which is majorly required to make your functional appearance for your SOC, or maybe use it for to execute your values, or to take consideration of your IO signals or your environment signals, etc. So that is the one which will be looks at is your analog and mixed signal blocks. So we looks more digital hardware, so minimum embedded software, very less AMS blocks. So because the consumption of power, the consumption of delay, reduction in an functionality will be seen majorly on AMS blocks. That's why we'll take in SOC very less space for an AMS block, very large space for a digital hardware. So to make the appearance of the digital hardware or to make more controlling actions, so we can have the embedded software over there, and it can be presented to those factors. So to make this, so we need to have a major area from 2010 to till today. We are going with a major bus architecture. The one best bus architecture, if you studied an ARM processor, is an AMBA. So that is a major bus architecture which will be uses your ASB and APB buses. So which makes a very good controlling on so all your system buses which is presented over there. So these, now we are all saturated, majorly saturated with this memory design. So these designs, AMS designs, processor design, etc. So your major end to be considered, and or you can say that indirectly we achieved something, all the performance factors to an higher level at these blocks. So only the blocks which is presented, so to achieve furthermore reduction in your delay, furthermore reduction in your um, mm, uh, um, power, etc., is with respect to these system buses or these bus architectures. We have variety of bus architecture which is goes on with that. So some of that will be your normal single bus architecture, or going with a distributed bus architecture, or nowadays we are looks at on more on wireless NOCs, etc. So once you are saying a bus architecture, so we look at on majorly on these synchronized blocks, because we have n number of components. All those, and nowadays we have n number of processing elements also, processor units also. So you can say dual to core, octa core, etc., quad core, etc. So all those cores should be very perfectly communicatable, so are very perfectly understandable to these components. So such that we need to have majorly a synchronized block, that is your clock, power, and a power distribution block. So majorly the clock will take its distribution with from the root clock to a tip of the clock, so where it looks at on a um, tree architecture, or goes with an H tree architecture, etc. So finally, our interest in this talk is majorly on a test structures. How well you can take up the test structure and how well it can be. So these test structures will lead to so many areas of interest. Nowadays, that will be the trend. The company looks for you people also to seek how well your become how well you will test the given block or given SOC or given a part system of an SOC, etc., etc., etc. To look at on these test structures, so we have a distribution on an SOC verification to an a design gaps. So that will take a major part and will seize how your parameters to be presentable. So the one thing is, so we have a small ASIC, we have a medium ASIC, we have a complex ASIC here. So the small ASICs will be at a lower end, so which will not looks more SOC complexity verification complex to be presented. Once you increase to an medium ASIC, so your major SOC will be goes on appearing, goes on burning, and which will be looks and verification complexity to be increased. Once you go to a complex ASIC, the whole SOC will be taken care. So and all the components of the SOC becomes the integratable complex values. So such that your verification will also be increases its complexity. So if you have one block, it's very easy to test. Let us say I have only one AND gate, so very easily can be tested. So I can push only an A and a B values, two input AND gate, I have A and a B values. I can say, so this is the Y is verifiable for the functionality given A and a B. But once you go for a three variable or a four variable value, so your complexity goes on increases. Let us say if I have an n variable, what is the complexity? It is a 2 to the power of n complexity of the verifications, because you have an 2 to the power of n input combination to be checked for the appearances, for the output to be derived. So such that your complexity is increased to an 2 to the power of n. Let us say if I have a p complex values, p functional values, all p functional values will take an x complex parameter. So then my appearance or my complexity verification complexity is an 2 to the power of p plus x values. So how much is it? It is increased. So that's why. So the major complex ASICs on an SOC will make a higher verification complexities. So normally these medium ASIC and a complex ASIC will looks its performance. So with respect to how good you can able to simulate that. So that's why we have an event-based simulator. We'll look at on what is an event-based simulator, how it can be taken. So cycle-based simulation and hardware accelerations, hardware simulation accelerations. So you at initial stages, you will have only an event-based simulation. You will check only an event values. Afterwards, you will go to an cycle-based repetitively. You are going on checking the given functionality for different conditions, for different environmental values, etc., etc., etc. So, and you looks the performance for an different factors. So with respect to that, you will create an acceleration. So then you will check for those hardware accelerations. So for the given SOCs. So as your design gaps is goes on increases, your complexity is very more. As the complexity is very more, so your SOC performance is also goes on decreases with respect to the simulation factors. So now how to make this verification very perfect, very gives an higher simulation performance values, etc., etc., etc. That's why your verification itself will be segregated into a different optional values. So what is an using an simulation technologies? So you can use an static technologies, you can use an formal technologies, physical verification and an analysis. So SOC will looks all your verification. So with respect to these factors. So one is the simulation technologies. The second one is static technologies. In a simulation technologies, you will just check the functionality You will just check how much code you are written will be coverable, how much your input values will be derivable and output, etc. In static technologies, you check for the timed factors. Let us say at a time t1, my input A is goes from 0 to 1. At time 2, my input will be goes from 1 to 0. So I will check the static appearances of my values at t1, at t2, etc., etc., etc. I will see that what is my propagation delays for that. So that is my static technologies. In a formal technologies, so I will see how much my SOC components will be presentable in a different functionalities. You checked only the functionality of each block. You check the functionalities of the whole SOC through an assumption, but not with an
Hello? Hello? Hello, am I audible?
Yes, ma'am, you are audible, but sir is not audible.
Professor Shashidhara, you are not audible to us. Hello, sir? Professor Shashidhara, you are not audible to us.
averages.
Professor Shashidhara,
Yeah,
your
yeah,
voice is not audible. Professor Shashidhar, yeah, now you're audible, please. Please. Earlier you were not audible for 2-3 minutes. Please carry on.
Hello, sir. Professor Shashidhara, can you hear us?
Yeah, now it's clear, right?
Yeah, now it is clear, but you need to increase the volume. It's a little bit slow.
Goes on with that. So the simulation technologies will be goes with an event-based simulations. So you have an AND gate. You are checking an AND gate. So you have an input A and a B. At time t1, you are change the event from 0 to 1. At time 2, you change the event for B as an a 0 to 1. So the changing of the appearance of input A and input B at time t1 and at time 2 is called as an event occurrences. So these type of simulations, so where you are changing your input appearances for every time period and you are checking the functionality to be verifiable. So those type of simulators will be called as an event-based simulators. So let us say for a particular time period, I am having a some of the event to be occurred. Let us say at time t1, I have input as an a 0, 0, 0, 1 and a 1, 0. At time t2, I have an a 1, 1, 1, 0 and a 0, 1. So this repetitive time period checking for the given functionality will be called as a cycle-based simulators. So the third one is a major one, so which is normally appears at an abstraction level. So where you look at on for majorly on an uh, um, uh, how your input signal will be considered to your system and how it can be derivable. So normally we look either in an event or a cycle based. So the signal will be taken as an event and it will be presented to your system and taken as an analyzable part at your output values. But in a transaction based simulators, you will give the input as an a transactors, as an a tokens, as an a time based signals. So, and we'll analyze or we'll ask the system to execute that and take an values. So normally there is a two types of transaction based simulators. One is a timed transaction. The second one is a non-timed transaction. So in a timed transaction, for every time period, so your cycle of input is goes on changes. You have a time t1, so a set of, let us say, input A will have 1, 0, 1, 0. So at time t2, the input A will changes to an 0, 1, 0, 1, something else. So that the appearance of input A to your system, so as an 1010 or 0101 at T1 and at T2 will be called as a timed transaction simulations. So in a non-timed transaction simulation, we particularly given A as an A1010 and it will be appeared to your system and validated at output end. So there is no time limitation, there is no timed appearances values. So those type of transaction simulations will be called as a non-timed transaction simulations. So normally, so if we are doing it an abstraction level of design, a higher end designs, at a system level designs, we looks more on transaction based simulators. So normally we will use a system C to do that. So event and a cycle based normally will goes with a test benches. So you can utilize the system Verilog or you can go with a Verilog itself. The third factor, the fourth factor, which is more important for my analysis or for my design, to be appearable as a block or as a system or as an the component. So that will be with respect to how you very effectively you are explain your logical values. So the thing is, so you return if statement. So you had created a three nested values for that three nested conditions. Are you going to check all the three nested condition under the given if values, under the given if values? So in the given period of functional parameters. So if you are covering, then that will be called as a code. The fully logical code you are explained is covered. Otherwise, no. Right? So you have the another one example is if you are written as case statement, let us say case switch one. Case is a switching statement. So S1, S2, S3, S4. So we are checking for all the S1, S2, S3, S4, including the default, is executing for your system or not. So if it is executing, then we call this a fully code coverage for that case statement. Otherwise, how much case values or how much switch values you are considered, so that many percentage will be considered. So there is their appearance for your systems. Normally, all your logical expressions will be looks more on these factors. So how well it can be presented and how it can be considered. So the fourth one is majorly with respect to a higher end or complex SOCs. So as we had in small embedded systems where only a logical implementation will be seen. Similarly, we have a small ASIC where you look for a small values to be or small to be verifiable. If you go to a complex SOC or a complex embedded system where you have a hardware and a software. So here also in a complex ASIC, we have a hardware and a software, and more those two needs to be integratably verifiable. You can have a separate verification, a unit test verification or a integrate test verification for an hardware and a software separately. But co-verification by combining the hardware and a software will take a major part. There may be a large hardware, there may be a small software, and vice versa can also be seen, but the verification should be taken. So normally these type of verification will be looked at on a platform based. It's where we need to create a platform when we need to have a platform and it goes for an verification. So the one such type of simulation platform is your ISC simulator. So that verifier, etc., etc., etc. So in some cases, that
Sir,
emulated.
again,
Pardon?
the voice was not audible, that's what. Now it's audible, sir.
Okay. It will be takes an emulation system and verifiable. So the next factor is a rapid prototyping systems. We call it as generally an RPS. So if some of the hardware needs to be presented at an early end or at a final end, so which may be considered to an IPs. Maybe in the tomorrow's session, I will describe more on rapid prototyping systems where I can look for majorly on so the IPs which is considered at an early stage at an final stage for an equal verifications. So accelerators, so there is a major end we look for it also. So because all the systems, all the subsystems what we are designed, what we are taken care may not be elaborated or may not be presented well, may not be taken care to show higher performance values, maybe and may not be speeded up parameter. So that's why we look for these type of accelerator to boost your system to a higher level. So these are all for your hardware and a software, digital hardware and a software, what we are described. So the final factor is an AMS simulations. So I'm not much concentrated with the AMS simulation because I looks the above factor as a major factor because I have a huge digital hardware, so a little embedded software and a very less AMS block. So that's why so major concentration may not be given to an AMS simulation, but we have an Verilog AMS, VHDL AMS. You can do the AMS simulation using your normal simulators. So what all event-based or cycle-based simulators you have. So for an AMS simulations also. So in static technologies, we have two varieties. One is a linked checking. The second one is a timing verification. So in a link checking, we will see the correctness of your logical explanation. You return y is equal to a and a b. How well this syntactically the a and b is correctly mapping to an a y is checked here as an link checking. It is not a compiler checking. So it is a functional appearance checking. So maybe considered with the one factor and may be presented with other values. So normally it will goes on identifying some of the lint errors, which may be a very simple and which may be a presentable towards other factors. So static timing verifications. So we have a different timing parameters to be verifiable. So one is an setup time, hold time, delay time, etc. Depending on the requirement which is taken care and which can be presentable. So which will be goes with this setup, hold, and a delay parameters. So the major challenging is at the static timing verification is a multiple sources. If you have n number of inputs, n number of peripherals, n number of output to be derivable, so then these multiple sources set the whole pattern. Normally the formal techniques block checking, or we call it as logical appearance checking for each block may not be known as a white box values, may be known as a black box value. That you can see at these formal values once again. So we have different formal checkings there. So one is an theorem proving things, where you look for proof based or not proof based. Some of the lemma appearances are taking care of the lemma to be proven. They were doing some neural network. You need to check level 1, level 2, level 3 neural values to be available.
Hello? Professor Shashidhara, you are not audible. I think there is some disturbance at your end, sir. Hello? Professor Shashidhara, you are not audible, sir. Miss Gayatri?
Yeah,
Hello?
good morning.
Yes, ma'am. Can we do something? Actually, I think there is some network issue at the end towards Professor Shashidhar.
What you
Now, madam, is that clear?
Madam, can you ask him to just disconnect and again rejoin the meeting so that the network can be okay?
yeah.
Thank you so much. Participants, please hold on. There is some issue, so we are trying to resolve the issue.
Is it now audible?
Yes, sir. It's
Hello?
audible now. Yes, sir. Audible, sir.
Can you make me as a presenter?
Yes, sir. Uh, Prashanti? Prashanti, can you make sir presenter? Prashanti?
Yeah, sorry for the disturbance. So maybe some network issues. So this type of proof you are checking. So normally the proof checking is with respect to a, a manual end, not with respect to an automatic end. So why it's not to be fully automatic? Maybe some parts can be checked through any simulators or some of the formal checking tools. So, but not fully with respect to that. So because of some parameters which will be looked at on uh, to map those values may not be appearable. Your lemmas may not be presented well. So that's why it will not be a fully automatic. So you're going with and some of the factors to be so the second one is a model checking, formal model checking. So in formal model checkings, we are going with your model to be presented and it will be considered at a block level. Maybe some parts at a component level also. So that depends on how you, segregatively you looks for that. So we have a separate executable tools for these type of formal verification. uh, where you looks at on the different models to be appearable. I think so. In the next classes, I am going on, or next sessions, I am going on exploring more on these model checkings and how it can be taken care, how it can be well presented, etc., etc., etc. So the last one is a very important one. So where you will make sure. Hello, where you looks for the more comparative analysis with respect to a reference design and with respect to a modified design. Let us say, so those type of analysis will be called as an equivalence checking. Let us say, I have designed an A1 system. So afterwards, it requires some modification as per the spec or as per the requirement. I have modified it. So now the reference design, the previously designed will be taken as a reference design. So that design will be compared with this modified design and make it appearable, make it comparable. So these comparison needs to be equally mapped, the functionalities, the parameters, the constraints which is defined to that and taken care at a modified design or not. So what are all the differences you have? So that one only can be made appearable for other formal verifications, not fully. It's because your reference design is already verified. So that's why what are the different factors which is there in the modified design will be taken to the further verification, so that your time to design will be reduced. That is the major end. So it will be looked at on to those factors. So some of the equivalence checkings, you will do it as an RTL to RTL, RTL to gate, gate and a gate implementations. So, and the major thing is, so in formal verification, majorly on equivalence checking, we are not dependent on the time, or no timing verification will be done. It is only checked for which is appearable, yet the reference design to the modified design. So only those factors. It is not with respect to other parameters which is considerable to those parameters, those appearances. So the last one is a physical verification and analysis. So there is so many issues which will be considered for an physical verification, like timing, signal integrity, a crosstalk, maybe an IR drop, so maybe an electro migrations which is looks at on, so maybe an a power analysis, so maybe an a process antenna effects, so goes with an a phase shift masking, optical proximity correction, etc., etc., etc. So here some of them maybe depends on the physical parameter, some of them may not be presented on the physical parameters. Let us say, so if you are taking a timing, the timing normally with respect to the signal, which is the input or output, the IO signals, which is taken care. And the second parameters which is looks at on a timing is with respect to the channel length, channel width you are defined. So the power you are inputted to an source end, VDD, VSS end, etc., etc., etc. That depends on how you can take that physical parameter to be verifiable. The signal integrity maybe looks at on a, your input buses or buses, how it can be taken care towards your design, or the interfacing of your bus to an design, how well you can able to transfer the signal present at a bus to an design and design to an bus. So that interfacing will make an signal integrity to be explainable. So there is so many factors also once you are routing a bus, buses, two buses parallelly. So you can have some of the integrity to be checked also. So many factors. So the crosstalk is the one whenever you are routing a parallel routable routes, either it may be an a power or it may be an a ground, power and a ground, maybe a signal lines and a power, signal lines and an a clock, etc., etc. So will makes more crosstalk. So once the crosstalk is appearance, so your noise level is introduced to your system, so that noise level goes on reduces, so the signal strength of your system. The third factor, the fourth factor is an IR drop. So once you are taking at an interface end or taking at an routing end, so there may be a current driven resistances or an IR resistances are will be created. So which makes more voltage effect. So those type of effects will be an IR drops. So we look at is another one effects which is considered from above factors. So the power analysis, so up to this point, so normally we look at an component, and below is a it looks because as so we so the phase passing the we have an function
Sir, we can't hear you, sir.
Sir, it's not
Sir.
audible, sir.
Sir, we can't hear you, sir.
Professor Shashidhara, we are not able to hear you, sir. Hello, sir. Gayatri, can you please call if you have contact numbers?
Yeah, I just asked for the contact number. I don't have. I'm checking. I'm trying to get it, and I'll do that.
Thank you so much. Please resolve the issue if possible, as soon as possible. Sir, we can't hear you. Professor Shashidhara, we are not able to hear you, sir.
Is it now?
Yes, sir, it's audible.
Hello?
Yes, sir, it's audible now.
Yes.
But
Yeah,
Professor
thank you.
Shashidhara, you are not audible for last about 3-4 minutes.
Yeah, I just checking my network. Somebody told I'm not audible, so that's why.
Yeah, yeah. Please.
Sorry for the disturbance. Yeah.
No problem, please.
Why it's not sharing now? Already shared. Huh?
Slides are not visible, sir. I have given you the
Yeah,
presenters. Yeah, you are presenter now. You can share the slides.
I'm unable to share the things.
I think the network is weak at this end.
Yes, sir. He is again out of the meeting now.
Ms. Gayatri, can you ask her about the slides to be sent to us? We can actually.
Yes, sir. I'm just contacting. I'm trying. I'm connecting to Ganesh, sir.
Sure,
And
sure.
I'll just give you the details.
We'll ask the slides to be mailed to us, then we'll host it. We have a
Yeah,
good.
sure. Yeah, I'll.
Thank you.
Yeah, madam, I'm just connected it. Yeah. Can you mail me your mail ID? Yeah. Sorry for the disturbance. Now I think my screen is visible.
Excuse
Hello?
me, ma'am. Hello. Yes, sir. 1 minute, sir. I just want to ask their email ID. Ma'am, can you give your email ID so sir can share their his PPT to you? MNIT?
Yes, madam. I am writing.
Yeah. Thank you.
Sir, I have shared the email ID. Please share your PPT on this so that your it seems your network bandwidth is not good, speed is not good. So if we are going to share the PPT, then it will be you'll be having the bandwidth to speak well. I have shared you the email ID, sir. In the chat box, you can check it, sir. Yes, sir.
Yes, sir. We can hear.
We
Yeah.
can start, sir.
Now,
It's yeah.
yeah, I'm just going on with that. So if any problem is there, let me know.
Sure, sir. Yes, sir.
Yeah. So the event-based simulation, so to up to an emulation. So the total will be with respect to a functional verification. So the formal verifications may not be takes your functionality to be checked. At an abstraction level, so we'll look at on how well how your abstraction will be seen. So normally, so the event-based simulations will be goes with your behavioral RTL and a gate level checking. Cycle will goes only at an RTL and a gate, so up to a formal verification from a cycle base. But an a static timing analysis more looks at an a gate, because so you looks at on the timing values to be presented at each gate. That's why it looks at on a gate. The functional equivalence will be presented to all the level, but STV will not checks that, because STV not request to that also. So that's why, so it will not check the parameters, the functional equivalence values. So the timing will be goes with only with an event, only adware accelerator and an STV. So other parameters will not check for any timing, because all are bounded values. These three, other three are non-bounded values. So that's why we will not check for that. The gate capacity will be very high at formal and an accelerator end, very high at an emulation end, because so where you look at on more factors to be seen for those values. Runtime will be very high for an STV, because which looks more time dependency. So the acceleration and a cycle both are repeatable. So that's why it will take an 1 kilo cycles. So for a normal design, so for an emulation factors will goes with an 1 mega cycles. So the event and a formal verification normally very low cycles, and it will be not presentable at a very perfect runtime factors also. The emulators will having very higher cost, because that should be borrowed IP, or that should be executable IPs, verified IPs. That's why the cost will be very high. So in other factors, the cost will be very medium or very low. So depending on how it can be taken. But in STV and event based, no IPs will be used. So that so there is a lower end, so which can be seen for a cost. So lower cost will be 6 for that. So comparing hardware software co-verification options. So if you are using a instruction set, there is a medium speed, normally uses a C model, goes with an algorithmic base. So hardware software co-verifications will be very slow speeded, because it should have to directly verifying the hardware inside the software, or software binded with an hardware also. So more time dependent, more debugging nature for an hardware and a software. the real-time parameters can be used. Rapid prototype, so the timing will be there very fast because the rapidity will be used, or RPS will be used only for to increase the speed of verification. So that's why so we looks for more speed one, more real parameters, more real time software which will be used over that. The emulations is very high, very high cost with an very fast in nature, because the rapid prototype normally uses an IP. The emulation is a separate entity which will be utilized. So that's why it's very fast factors to be presented. So you can choose your option here. So depending on what you want and how it can be taken care. So we can't describe it which is the fastest option you have and which can be considered for you also. That depends on how it can be taken care to be presentable. So normally it will be goes with a different design factors or design models, what variety of design models you go for an verification with respect to that. So normally, so an event-based simulation is best for asynchronous small designs, where you look for a small time and non-time dependent designs to be tested, where you can see more event to be appeared. So the cycle based is very good for medium sized designs, both synchronous and asynchronous, best for that. So because where you look for more repetitiveness, so that will be seen over there. The formal verification, so it's best for control oriented designs, where you make more appearances on uh, the different factor of a design. Let us say I have a processor, I have a control unit to control the processor. So at that time, so we can go for control oriented design. And so where you look for more hardware to be integrated, more block level designs, so will be looks for the formal verification. So the emulations will be used for large capacity designs. The dependentability and independentability both are presented at this end. Rapid prototyping, best for software development, where you can make the integrative software to be presented for an hardware. Integrative software means two different software blocks will be integratively appearable at a single hardware. So at that time you will go with a rapid prototype. So normally best suited for the software development cases. Methodology which is used for an SOC verification. So we look for the system level verification. We look for SOC hardware RTL verification. So software verification, netlist verification, physical verification, and a device test. That depends on how well you can taken care to do this. So in system level verification, you look set on this whole system to one end and it can be presented. In SOC hardware verification, RTL verification, you look for the logic to be presented, how well it will be goes on creating an hardware, how well the logic is speaks on your modeling style, etc. The software verification, normally we have varieties here: integration testing, block testing, etc., etc., etc. So that is taken at a lower end and it can be made it available. Normally we'll go with the performance testing and unit testing of an software and we'll do it that. Netlist verification, synthesized verification we generally call it as where you can have more constraint based design, and for that constraint based design how you can able to generate a netlist and how it can be verifiable. Finally, we'll go with an APDs, the physical verification. Looks at on the post to pre-routing, post to pre-CTS verification techniques, and it will be taken to be a presentable at a different times. So the final one is a device test, that is an AM manufacturability test. So that will be looks for more value-based appearances. So SOC will take the specification. The major end will be look at on that. So we'll have the SOC to be specifiable at a different hierarchical levels. So yet those hierarchical levels will design the system. It is not at single end you looks at on. And each hierarchy level will look for different IP to be presented and looks at on software IPs and an RTOS libraries. Let us say I am doing a biometric integrated biometric verification. One is a finger, the second one is a face or an iris. Let us say for the iris, the segmentation is required. For a finger, pre-processing is required. So I will segregate my hierarchical specification to do the finger analysis and an iris analysis. I will design my system for to do the finger separately and the iris separately. Let us say I have some IPs to do my segmentation, maybe a threshold based segmentation or a canny segmentation, edge detection and a segmentation, etc., etc., etc. I will segregate that and I will utilize that as an IP, hardware IP. I will present it. While doing that, I may require some of the real-time factors, maybe an algorithmic processing. If I'm using a canny edge algorithm, so I want to extract the edge. So that edge for both pre-processing and a segmentation, I want to extract the edges. I will do with a software. I will present that as an integratable hardware IP to my systems. So that's what my total system design will be pursued. So that system design will be again partitioned into an hardware and a software. While doing a system design, to partition this hardware and a software, we'll take care of the verification that we call as a system level verification. So in the system level verification, the whole system will be looked at on a single line and verifiable, right? Verifiable. How well you are taking to verify it, how much uh, the test vectors you are generated, how much the data will be presented to that, so will be considered here, and that will be makes us separate to the hardware and a software. The hardware normally goes with an RTL. The software normally goes with an software development and its verification, and it will be presentable. The RTL will take initial to an, and from here it is goes to an ASIC flow. So you look at on the ASIC flow. So you have an RTL design, you describe design, you will do a functional verification, you do a synthesis, generate a netlist, verify it. So then you do a constraint addition to the synthesis, you do the netlist verification. Goes for an a PD. So do the functional verification. So pre-routing, post-routing, pre-CTS, post-CTS. So pre-synthesis and a post-synthesis. And this is the pre-synthesis factor. So this is the post-synthesis factor. So there you will check for functional verification. Post, this is the pre-synthesis functional verification. This is the post-synthesis functional verification. You can have a timing. You can have a physical parameters to be verifiable. So to seek the performance values, to seek the design constraints, to take care of the device tests, etc., etc., etc. Generate the design factors. Goes with an sign off. That is the total design sign offs what we are presenting it. How do we do this verification? You can do with a block to a system to a block. So varieties we have. So that is what top down verification. You can go from top module to a down and do the verification at each level. You can go for bottom up. You take a block, you do it the verification. You integrate it, you do the verification, you come out with an system. Platform-based verification. Some of the verification is requires a platform. Some of the verification may not be required on a platform. So that depends on what verification you looks for in a platform, what verification you looks for an a non-system values. So with respect to that, so you can segregatively explain so those values there and make it appearable also. System interface driven verification. So you have a part of the system which is designed, a part of the system which is taken as an AIP, emulation, RPS, etc. So at that time you will interface that system with these driven values and goes for an A verification. Those type of verification will be called as an system interface driven verifications. Top-down SOC will have an verific spec. We will go for an design with an IPs, software and an hardware IPs. So you will do the system level verification, partition it, do the functional verification. So partitioning is itself hardware RTL model. So that RTL model without any constraints, you are doing a functional verification, may be called as an pre-synthesis verification. Do the synthesis with constraints, meet the constraints with netlist verifications. So there you plan, there you place, there you make a design implementable. So goes these plan, place, and a design within a routing as an APD, and then do the post synthesis functional verification, do the timing analysis, different timing analysis. So which is to be presentable and not to be appearable. So takes care of the functional parameters and then finally goes with a device test. So that is the appear design with an sign off. If you go from system to the sign off, system to a block level verification. So that verification we call a top down verification. Similarly, we have a bottom up design. We have n number of design files, looks at a component, looks at a blocks, looks at an unit. So we will do the front end acceptance. We will take that to any different levels of testing or as a verification, or goes with an abstract model view testing. So in a detailed design view, we will look at an level 0 where your components, blocks, units will be tested, and then go to the level 1 testing where your memory map and internal interconnects will be tested. In level 2, you will go with the basic functionality and external interconnect to be tested. Level 0 to level 1 normally as an abstractal view. So you are testing independently from level 0 to level 1 to an level 2, and makes your design verified and validated for the given values. At a level 3 testing, so we have totally integrated system from the different components integrated, different blocks integrated, different units will be integrated, or called as a different subsystem to be integrated and make it appearable. So there you are doing a testing called as a level 3 testing. At the bottom up SOC, normally this will be the major end. So which will be looks the design. Maybe you can have an RTL configuration. You can have an RTL2 gate configuration, etc., etc., etc. And these analysis will be the basis to do other verifications. So afterwards, you integrate the system. Once you integrate the system, and do the synthesis. This is your pre-synthesis factor. Do the synthesis with an constraints, generate the netlist for the system, so and do the verification. So then go for PD with an planning, placing, designing, routing, etc., etc., etc. Do the post synthesis functional verification. So do the pre and a post routing verification. So pre and approve post CTS verification. So with respect to that, you do the timing, physical and a device test, and then sign off. You can see there, we started with the components, we come out with a system. So that's why it's called as a bottom-up verification. So in the previous case, we had a system, we partitioned it as a blocks, as an units, as an subsystems, and you verified that here, right? So that's why it's called as a top-down approach. This is a bottom-up approach. In a platform-based design, we will create a platform for your test. So this is the SOC platform, maybe utilizes top-down, maybe utilizes bottom-up. So this platform will takes the predefined values or the predefined test vectors. So that will be boosted to your SOC platform or your platform and goes for a verification, different types of verification. So to hold this platform, we need to have a high performance parameters or and peripherals. You can insert those test vectors or you can segregate the platform with an general components, high performance blocks and then peripheral blocks and go for different testing. This is the one platform, this is the one platform, this is the one other platform. So you can have a system bus and a peripheral bus to communicate between this platform to this platform, this platform to this platform. So that your interconnect verification between the SOC platform is verified. From here, we are going for the synthesis process and you will do the synthesis parameters. So these are the design derivative blocks, so which will be utilized as the verification at a higher levels. And you can utilize new added IPs also here, which is verified, no need to verifiable. So if it's not verified, so then you can verify with respect to your design, derivative design, and make it appearable in your derivative values. So system interface SOC design, where you create different blocks. Normally it is called as a block derivation. So some of the blocks may be an interface model. Some of the blocks may be your designed model. Or you are going with some of the blocks to design at the current appearances, which may be dependent on other blocks also. Let us say I have a block A, B, C, D, E. So E is the designed block, which is depends on the block A, B, C, D. So those are all will be called as an interface model. This will be called as a design model. So all these blocks will be segregatively insert or drives their values whenever the block E requires for to test. So that the interfaces, the system interfaces will be drives to your block E and it will be tested out. So these block A, B, C, D may be tested one or may not be tested one. So if it is a tested one, this block E will be validated. Otherwise, the block E will be verified after testing these interface models. So then the block E is equivalence, made it equivalence checking and then validated for those values. So device check, to check if devices are manufactured defect free. So where you look for the DMT to be taken care, design manufacturable testing, where you will focus on the wire connections, where you will focus on gate truth tables, where your function focus on not functionality parameters. Depending on that, so the values will be taken care. So the challenges in SOC device test, the test vectors are enormous. We need to have enormous test vectors. Different environmental test vectors needs to be generated. So there is a major factors which will be looked at. And we have an ATPG, automatic test pattern generation, but still that is not most effective uh, to generate these enormous number of test vectors. So let us say I have an n bits of inputs. So then I need to have an 2 to the power of n combinations of your test vectors. That depends on how it can be uh, taken analyzable at the different ends. Core forms, we can have a soft, firm, hard, uh, different forms, and each will be utilizes uh, the test cases or the test vectors. So the cores may be an logical core, maybe an a memory core, maybe an AMS core. So depending on that, so uh, to be considered for the other factors. So accessibility, very difficult or an expensive. So it depends on how it can be taken care. So the difficulty is seeing the physical factors. Uh, and another one thing is if device fails, so then you need to go back and redesign it. The cost invested up to and manufacturability may not be appeared to the design values. So your test vectors may not be appeared to the design values. So that's why it will becomes more expensive at that end. So there is a different strategies to do the DMT. So one is an logical based built-in self-test. So where the stimulators are stimulus generators are embedded, response verifiers are embedded. So memory based on-chip address generator, data generator. So read write controller. So which will be uses some normally a memory test algorithms to do that read write controller testing. So that is the one end where we looks more on the factors to be implementable. Mixed signal based for AMS course. So ADC, DAC, PLL. So normally we look for more on conversion factor, integrators, uh, differential and integration parameters to be checked for a ADC and a DAC block. The PLL box normally looks for the range where the synchronicity can be presented. That is your lock range, capture range to analog range. So where it will be looked for that. So the scan chain, timing and structural compliances. So normally which will be those automatically with the ATPG tools, which generates and manufacturing the test values at a different factors end. So that's about the major introductory part on the SOC. Let us look at on some formal verification methods. So afterwards, I will wind up for today. Uh, I will ask the Shruti to continue with the System Verilog essential. So what is a formal verifications? An analytical way of proving a system is correct is called as a formal verification. So what is the analytical way? So you have defined y is equal to a and a b. So you need to see that the a and a b is correctly mapping to generate the y values. So there is no requirement for to generate a signal there, to input a signal there, or you are not able to create a stimuli for that. Here there is no test vectors to be inputted. Input test vectors will not be there. You are not creating test vectors. You are not doing any test cases also. You are just doing a deductive reasoning. That is a theorem proving. You are going with a model to model mapping. You are going with an equivalency between one model to the another model to be checked. So in a theorem proving, we'll use as an axiomos, rules to prove the system correctness, even lemmas called as an axiomos. So there may be an infinity which would be created on these lemmas once you are going for an proving. Will not guarantee that this looping, infinite looping may be terminated, because that requires a more dependable factors to be derived, one to one or one to many values also. So that it will becomes more difficult, more time consuming for critical applications only, which will be utilized for those factors. So the model checking, so which is an automatic technique, the theorem proving technique, as we stated, it is an not fully automatic. You can have an automaticity, but at a lower level, not fully automatic. So the model checking will be goes with an automatic techniques to prove the correctness of concurrent systems. We can have a digital circuits with respect to an to do that, or you can have different communication protocols to be presented. So there is another one, and we looks for that for your other mobile application or network applications or communication applications. So it can be tested for an real-time systems or an real-time embedded systems also, or control-oriented systems also. We have some of the explicit algorithms, so which goes for verifying these type of model checking. So the equivalence checking normally checks for if two circuits are equivalent, as we stated, the reference to a modified model. We can have an RTL to an RTL, RTL to an gate, gate to an gate testing. So that it will checks the circuits at a two different levels. One is at an RTL level, the second one is a gate level. Normally, the equivalence checking makes the differences between them, and that differences is goes for any testing. You can use that differences to construct a clock tree, or to seek that differences to do the clock tree synthesis, to do the scan chain insertion, to do the manual modification, etc. So what we require at this end is that the differences should be zero, so that we can go and make this equivalence checking 100%. So that's what the major aim. But you will not get an 100%. You will have lag between 60 to 70% from reference design to a modified design. So that difference, that is 30 to 40% difference, will make you to derive these three factors. So one to one or one to many. That depends on how it can be considered. So why formal verification? Simulation and test cannot handle all possible cases. So because the simulation and the test cases will takes only an a dependable factors than non-dependable factors. So you can use only some possible ones which are both dependable and non-dependable at these two ends. So, and they can prove still the presence of bugs, which will eliminate some of the bugs, but there may be still a presence of bugs. So those bugs is removed, or rather than their, which will be taken there for their absence values also. So these formal verification will go to for an exhaustive explorations of all possible behaviors. If verified, correct, all behaviors are verified. So if incorrect, a counterexample will be provided, a proof will be provided, and it will be takes to correct the non-equivalent or non-corrected values, and goes for a presenting those values also. So SOC, as we know that it's an high system complexity, so may not be possible to consider only the simulation and test. So if you go for those complexity to be tested, so the time taken to do the simulation and testing is unacceptable values. So that's why we'll make more time and efforts which needs to be devoted to an verification than a design. So that's why we requires more number of engineers at an verification and than at a design. So the design end will require a less number of people. The requirement is very less, but the efforts and the time is requirement. The verification end is more. So that's why we makes 40% to an 70% of verification than in a design values. So nowadays we have so many automated verification methods. So but not effectively. We use a quantitative analysis than the qualitative analysis. So you can have a quantitative product than the qualitative product. To do the qualitative product, need more and more automation algorithms to be implementable to any of your CAD tools or any of your design, so that it will be verified at a higher level also. So that may be integrate your automated and unautomated process to be presented in your design processes. So that is the one factor which will be looked at. So how these load will be maintainable? So at different simulation parameters. So we have an 100K gate count. So we have a 1000x more vectors so required to validate. So as the number of gates goes on increases, so still today this is a valid factor because the load on a simulations will be the same factors which will be goes on derivable 100 into 10,000 to 1 million times. So more simulation load so can be expected and which will be made available also for those values, so that your simulation load as and when your number of gate count is goes on increases, number of complexities goes on increases, so our number of transistors inclusion is goes on increases, so your test vectors or the simulation load is goes on also vector increases with respect to the test vector parameters or the validation of the test vector values. So why formal verification now? So examples of undetected errors. That is what. So this is one example. I'm talking to see why formal verification is now. Arraign 5-rocket explosion in 1996. Exception occurred when converting 64-bit floating number to a 16-bit integer. So we thought that in functional verification it's very good. 64-bit floating number is very perfectly converting it to a 16-bit integer, so that the explosion will be taken care. But the major thing is the multiplier table, which is derived at an Pentium FD4, which is not fully verifiable. So that is having a bug. So that's why your explosion is not properly met there. So that will be makes the failure on 5-rocket explosion factors. So that is what the design failures will be there if I am not doing a formal factors. So what tasks for a SOC for the verification? You can have an equivalence checking, you can have a property checking. The property means model checking. So we will make some assumptions, the properties. We will take the model under test, check the satisfaction of these properties. Is it appearable? Is it taken care? Is it makes the my model to be convertible, etc., etc., etc. If your check is satisfaction, then you go to yes. Otherwise, you repeat this. In equivalence checking, we have a reference model and a model under test. We will check the functional equivalency between this and this, and you will say yes or no for that. So, in property checking, so we will take the properties of the reference to a model, and you will check those in another one. So for this, it will be a reference design. So for this will be an equivalent design model. So if it is fully property checked, so you can have the property checking at the gate level, etc., etc. So in equivalence checking, you will check the RTL to an RTL, RTL to an gate, gates to an gates, and gates to an RTL, or RTL to an gates, RTL to an gates, etc., 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 to make your design factor to be proved for their equivalence values. So the property checking normally based on algorithmic method for verifying the correctness. So finite concurrent systems. So we'll have a temporal logic specifications to do that. So we have a practical approach to formal verification, so which will be derivable to satisfy those values, the logical values, and make it available also. What is necessary for model checking? A mathematical precise model for the system. We need to see that how precisely all your logical explanation is mapping. So that is a major factor. And each model should have to describe their properties. So that is a language to state the system properties, how well it can be mapped. So that will be describable at every end you are making. What you are using a Verilog, it should be describable. If you are using a System Verilog for the design, it can be describable. So now we will create a method to check this. So to satisfy the system for the properties you are defining, you are just mapping it, the properties with the system, and then it will be says how much it is verifiable for those factors also. So normally we will utilize the FSM systems. That is the best thing which will be goes for that. So that is the one formal model of the system. So that's why we majorly think on how FSM, effective FSM can be designed. We have an CFSM, communicating FSM. We have an reduced FSM. We have an ASM, algorithmic state machine. So all those are derivable from the FSM. So that we need to know how the finite state machines are derived and how it can be. And each state what you are expressing at these FSM need to show their behavior with a set of properties or specs. So for example, each state needs to be depends on a logic. So that logic may be derived from some other else or may be derived from itself. So that's why those type of logic will be called as a computation tree logic. So every state you are defining for their input and output values or for their transitions is should be with respect to these logic or CTL values. So to compare this behavior or to make this behavior to be appearable for these properties, we will create a method. That method itself will be called as a model. So we are checking that model for the states or for the formal model for their properties to for appearing as that properties will give an efficient FSM traversals. So that is the major end which will be looks or which the major things which needs to be looked at on. So formal models of the system, any mathematically precise model that can be presented as a state transition system will be goes with an FSM, Petri-nets, timed automata, timed Petri-nets or automata parameters, state charts, ASM, etc., etc., etc. That depends on how the state transitions will be needs to be considered. So this is the one normal state transition system. So it will call as an K structure. So here I have three states, S1, S2, S3. So there is a transition which is occurs from S1 to an S3, S1 to an S2, S2 to an S1, S2 to an S3, or S3 to an S3 itself. So this is called as a translational relations. This is called as a translation relations. Each translation relations to an state will be appearable with respect to the logic defined at each state end, that is A, B, and C. So that each model which is created for a state transition system is a set of state, relation, and a logic. The state may be the states, number of states defined here, S1, S2, S3. The relation which is states how to communicate between the transition communication between S1 to an S2, S2 to an S3, and vice versa also. And the logic which is sees the relation with the states as an ABC values. Or each state needs to define their relation, transition relation for the defined logic. So that is called the logic. Each property which is specified through a language, which is sees and temporal linear temporal logic called as an ALTL. So each transition of a state is linearly appearable, one to one dependent, one to one dependent. This is called as a linear temporal logic. So computation tree logic, which is derived from a root of the system, goes the dependability to the furthermore. Each state or each link which is derivable, so derives a multiple dependabilities also. So this is normal way or computation tree logic. If each dependability is with respect to a time values, let us say this will be derived to this with a T1, this will be derived to this with an T2, etc., etc., etc. So these type of dependability to derive a logic or a tree logic will be called as an timed computational tree logic, TCTL. So that's what less than 7 millisecond, etc., etc. You can define it. CTL will be goes with a path qualifier where you will seek all computation paths. You need to explain it how all computation paths are exitable and which makes the verification verifiable also. So that's why we'll segregate my communication path, or sorry, my path as an all computation paths as an AA, for some computation paths as an EE. If all are computable, then it will be an EA. If some are computable, then it will be an EE. So there will be a temporal operators. So X next time and a next state, F eventually and a finally, G always and a globally, U until, or release or dual of U values. So there is a two formulas to define the logic, temporal logics, which is needs to be evaluated with respect to a state in the model. State formulas apply to a specific state. Path formulas apply to all state along a specific path. So one to many or one to one values. This is the traffic light controller, how it will be designed with that. I am taken a three lights, green, red, and an yellow. So each light will have a two states, one and a two, which specifies the path. We will sense the road, how many vehicles are there. So with respect to that, we'll set the lights, which defines the timer also. which formally defines your controller to be executable. I have two inputs, C and a T. C defines the turn on controller and T on a timer. If both are negative, I will stay back in the original condition, that is an G1 and an R2. If both are true, so then I will go to turn on the G to an yellow. I need to turn off the first path. This is the first path. 1 means first path, 2 means second path. So Y1 and R2. So after some specific time period, the Y1, the road path for 1 will be goes to a red and path for 2 will be turned to an green. So it will be there until my time period will be there in an or specified time period is appeared. So once the time period is expired, that is maybe in 10 seconds, 60 seconds, etc., etc. So then I will goes to the second state where the path 2 will be turned to an yellow. So and if both are goes to an negative, the controller and a timer, so then path 1 will be G1 and the path 2 will be G2. This is the simple crypt architecture. So if I am going on writing the tree structures or state graph, G1 R2, G1 R2, so G1 Y1 R2, Y1 will be goes to red and R2 goes to G2. So again R1, G2, Y2. So G1, R2. So it will be goes on doing it. Similar way how I can construct it. There are multiple values. The module checking, the safety condition, no green lines on both the roads. If I make it, then at the same time, then there will be a clash. So that's why I will take all paths should not be a green. That is G1 XORed with an G2. The fairness condition, one road has a green light. So that is an communicatable path or that is an executable path. So that is F, G1, so X node with a G2 values. So this is the total traffic light controller checking safety condition. So AG, G1 XORed with G2, EF, G1 XORed with G2. So yes, G1 XORed with G2. So that is a union 1 and a 3. So I'm marking 1, 2, 3 and a 4 states. So I'm just defining 1 and a 3 are the communicatable paths. So 2 and a 4 are not communicatable paths. So 1 and a 3 will be called as a green lights for either for G1 or for a G2. So 2 and a 4 are both are non-communicatable paths. So I will call this as a null states, which is a variable. Total states are 1, 2, 3, 4. So that's what I'm defining 1, 2. So that the safety condition will be an A. So fairness condition. So I can go from 1, 2, 3, or I can go from 3, 4, 1, right? So anyone. So I can go from 3, 4, 1, or I can go from 1, 2, 3, right? So my safety conditions, my fairness condition is at an 4 and an 2. So if I'm taking that fairness, if it is to be true, when this will be happens, right? So that's that my true appears for the green lights, which is presented at the state 1 and an 3. So that I'm going backwards. 1, 2, 1, 4. Sorry, 1, 2, 3 and 3, 4, 1. So if both are appearable, so going backward and stays 1 to an 3 and 3 to an 1. So then that would be called as a fairness conditional values. I think I have another 5 minutes or 10 minutes I will consume the time. Afterwards I will leave it out the session. So symbolic model checking operates on a set of states rather than individual states, which will be used normally on a BDD. So we'll discuss the BDD in the tomorrow sessions because which is more elaboratable. So with respect to the IP, which is definable. So represent cryptographic structures, manipulate Boolean formulas. So these are some of the tools which can be utilized for your academics. We have SFME, Mocha, WIS, and Hightech, STEP, SGM, RED, APAL, and Kornos. Some of them are open source and some of them are non-open source. So this will be derived by CMU, US Berkeley, Stanford, CCU, and Simca, Academica Sinsa, Uppsala, and Aalborg universities, Verimag universities. So communication tools, formal checking, normally will utilize and cadence at a companies. Model checker, Avante, formality synopsis. We have a separate tool to do the formalities. So that is through an synopsis tool. Formal Pro from Mentor Graphics, Black Tie or Conformal LAC, it's from an Verplex Systems. All are commercial tools. So industrial embedded SoC product, Korea Samsung Electronics S3C2 400X, ARM 920T processor, 16 functional modules as an IPs. We have a reused IPs for UART, I2S, USB, etc. So USB older version 3.2 is brought up as a new one. So there is a host controller. Designed IPs is bus controller and DMA. Normally an AMBA which will be used over there. These are SoC, STC2 400X, ARM, it is utilized the ARM 920 processor, memory controller, LCD controller, interrupt controller, test interface controller, bus controller. This is the AHB bus, DME, bridge. So these are the peripherals what I am utilizing it, bus controller and orbitals. This is the whole system. These are my blocks. Inside that I can have a components, units, etc. 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 So formal verification methodology which will be utilized is you design a Verilog, go to an SMV, model design, present the properties, CTL. So check the model checking using SMV. So if it is a fail, go for model design. If it's success, you take the design, optimize the design. So go for synthesis. So if it is using an IPs, so then your library should be taken care with the Verilog. This is the final generated netlist. So that will be considered as an IP. So that will be taken to an SMV where you will look for the model checking. So check the model checking, fails, do it again. So if it's passed, convert it as an IP, right? So you do the equivalence checking here. So optimize synthesizable design, equivalence checking with respect to this. So if it's passed, so then goes to the V or pass that to a synthesis process. If it's failed, so then optimize for your synthesis. At end, so we thought of formal verification of SOCs definitely required, but it should be used in conjunction with other verification techniques. Capacity of formal verification must be enlarged for its widespread adoptions. Technique 6 required for design abstraction and verification partitioning. So this is something on the verification. If you have any doubts on this, any clarification, you can ask me. Thank you. Hello.
Hello. Thank you very much, sir,
Yeah.
for enlightening all the audience with your very vast experience. So, yeah. So we are going to have our next speaker. Sir, you are the next speaker. So how you are going to take it, sir?
I am not taking it. So my research scholar Shruti will be taking it.
Shruti.
Shruti, are you there, right?
Shruti, are you there?
Yes, ma'am. Yes, sir.
I think Ms. Shruti will take it.
Yeah,
So,
I hope I'm audible.
yeah, you're audible.
Yes,
So,
yeah.
are you going to take it hands-on or how you are going to take it?
This is just a theory session for towards the
Theory session
introduction.
only. Okay, thank you so
Yeah.
much. So, dear audience, now Shruti has joined with us. Shruti is a PhD scholar with Professor Shashidhar. So, on behalf of EICT Academy, MNIT Jaipur, I welcome Shruti. in this program. So thank you very much for joining with us as a speaker. So now it's all stage is yours. Please go ahead, Shruti.
Yeah. Thank you so much. Thank you, ma'am.
Before that, if audience are having attendees are having some questions, please type in the chat box. We are going to take the questions with the Professor Shashidhar. If you have any questions, please type in the chat box. Audience, if you have any questions, feel free to type in the chat box, please. Yeah, somebody is asking to share all the slides and videos. Of course, we will be sharing after the completion of the course. No, not on day-to-day basis, but yes, at the end of the course, we are going to. Abhishek Tiwari, if you want to ask something, yeah, please let me know. Abhishek Tiwari, do you have any questions? So I think no questions from this side. So I welcome, I am very thankful to Professor Shashidhar and welcome Shruti. Now it's to you, Shruti. Thank you. Please proceed.
Yeah. Thank you so much. I hope the screen and is visible and I'm audible.
Yeah, screen is visible and you are audible. Please proceed.
Okay. Um, Good day, everyone. So I'm Shruti R, working as an assistant professor in the Department of Electronics and Communication Engineering at the National Institute of Engineering. Also a research scholar under the guidance of Dr. Shashidhara HR. Today I'll be taking up just an introduction towards the System Verilog essentials, like why do we need it. So the hands-on session for this will be done tomorrow. Today only the basics will be covered that will be helpful for tomorrow's session. So what we'll be talking mainly is what exactly is System Verilog and its major features that is making it unique, and also how is it different from other languages. Here I'm just going to have a basic comparison with the Verilog, as most of us I think will be aware of the basic usages of or programming any in hardware language, that considering that to be as Verilog. So what exactly is System Verilog that we are going to discuss is initially the language that we know, that is the hardware descriptive language that we consider as a VHDL or the Verilog, they are just the description language. But when it comes to verification, how are we going to verify this? The description that we have written in Verilog or VHDL, then we go for the language that is called as System Verilog. So this is actually called as HDVL, that is Hardware Description and Verification Language. Mainly this has the amalgamation of extra features, which is the features of HDL, that is it has the scripting features of Verilog and some features of VHDL, and majorly the object oriented programming concept. Hence it's a good amalgamation of the best features inherited from other languages. This is given the standard with an enhancement to the Verilog to 2001, in fact also to the extension to Verilog 2005 versions. So here this comes under, it is officially under the IEEE standard by given as 1364 Verilog 2001 standards. So we can in generally say it is having the extended features to Verilog. Okay. Coming to the thing, why System Verilog? So mentioned about some of its features, but what are its actual things that it supports? So mainly it is giving the narrow gap between the design and verification engineer. So here all the designs that have been done can be verified without any need of an hardware element there. So you can verify your design to its maximum level with high level of accuracy, because you have a very high level of abstraction available in System Verilog. Along with that, it allows you to integrate C model. So you have the most of the structures which are the data types, or the way in which you write, it can also be similar to your C if you are aware of that language, if you are very good or you are worked well in that language. It also gives us a support of the object oriented programming. Hence the programming flexibility is increased over here. There is a lot, some kind of restriction when it comes to Verilog that is been overcome with this feature. Now we need to kind of obtain 100% functional coverage here. That is, you want to have your design tested for all possible condition, for all possible stimuli. To have once it has been tested, then you can tell it is 100%, the functional coverage has been obtained 100%. Now to do that, you will need inputs, or you need the stimuli which have been generated randomly that can take all possible test cases. So that facility is available here with the constrained randomization. So the randomization that can be done here is by using certain keywords. As we proceed, we will have a look, just a glimpse of it. So once you have the randomization available, so you can give n range of values and can be tested for all possible conditions. Along with that, you need to give some kind of uh, inputs that can be used to validate your behavior of the design. So hence you are given the feature of the assertions over here. So these mainly will help us to check our protocol and also the coverage. So along with this, there is a new type of data type that is included, that is called as the logic. So there are many data types, but when we are familiar with Verilog, we usually work around or play around with the data type of reg and the wires. But here you are going to have a data type called as logic, which will which is actually giving us more features when it comes to System Verilog. So we are going to compare a few things in terms of with Verilog and System Verilog. So here what happens is, in Verilog you have design entry and module level verification, but in System Verilog you are going to have module level design, gate level simulation, even system level verification can be done. And mainly it's an you can also put this as an verifying language, that is, you can also put it under universal verification methodology. So anyways, the System Verilog is being the UVM is replacing System Verilog in the industry, but at the entry level, the base that you need to go for an higher level verification is being obtained by, or you can be satisfied by, the knowledge of System Verilog. Now coming to data types, the Verilog actually, as I told you about, it is mainly the usage of wire and reg type data type, that is a variable data type, and all these data types are having 4 states. But this system Verilog gives us the feature in which your logic data type is being used, so we need not worry about having the reg and wire. So also here you have two types of data types that can be of 4 state as well as 2 state. So 2 state is been introduced over here. When you consider logic comes under the 4 state data type, but still there are many other data types that can be included that will give us the features of 2 states. So the data type that are the 2 state data type will have the values of 0 and 1. Now what happens if x and z's are included during any of your simulation operations, or if the value that you give during the simulation to the design, what happens if x and z's are present in the test benches? So they are replaced to value 0 in System Verilog. Coming to its memory management, here usually when you design with Verilog, uh, here they are basically static in nature, so you don't you are using usually the fixed kind of arrays. Okay, the ranges are well predefined. When it comes to System Verilog, here also you have the features of the Verilog, that is having the fixed size array, or the size of the dimension will be defined during the compile time itself. Along with that, it provides you a feature that such that you can allocate the memory during the runtime also. So that means a dynamic nature or the dynamicity is introduced in System Verilog, which is unlikely present, not present in Verilog. That is an add-on feature. So we will be discussing in the slides to come regarding some of the dynamic uh, array allocation methods that are exclusively present in System Verilog. Having said this feature of the fixed and dynamic, the point of are they synthesizable comes into picture. So when we talk about the dynamic nature, so the dynamicity kind of the arrays, whatever we define, they are not synthesizable. Only the fixed size arrays, any operation that are done using the fixed size arrays, they are synthesizable. Whereas the dynamic kind of an array allocation, the addition, deletion, or any operation that are done, they are usually not synthesizable. When it comes to complexity, so the Verilog, if you are comparing based on the design structure, your Verilog design actually is slightly simple when it's simple when the design is of a smaller, but when you go for complex design, you need large number of RTL code here, so which will increase the verification process. But when it comes to System Verilog, so as you have very high level of abstraction, you can reduce the number of code, that is the verbosa can be decreased, and also you can have less number of bugs because with the abstraction levels you can have the verification done in the module level in an effective way, and it is also quite readable. When it comes to the port connection, you are usually we are aware of using named instances and positional instances in Verilog. Here you need not have that using these two only. You can also go with include device under the test by the symbol as shown there. So with that feature also, you can connect all the ports to the variables or nets with the same name as the ports. As I told you, the synthesis support, Verilog is well versed. Hence, the simulation and synthesis, you have excessive support available for it. But when it comes to System Verilog, you have a very limited synthesizable tool support, and moreover, when you use a System Verilog as a verification for implementation purpose, the well usage of the smart usage of the synthesizable constructs becomes a limitation over here. So that is one of the major hindrance in accepting System Verilog as the design language. Coming into the in concept over here, so you have as I have told you earlier, we have some kind of data types present over here, unlike our Verilog. Verilog also has most of these things. First thing is here we have reg. Reg in Verilog is of 4 state, but here we are going to replace it with logic, so which is also 4 valued. And next we have bit. Bit is data type in System Verilog, which is of 2 states, so it can take the value of 0 or 1. Similarly, you have integer I that has to be used in Verilog, which is of 4 state and that is of 32-bit signed. Similarly, you have it in System Verilog also, but you can call it as an int I, that can be of 2 state in System Verilog, and that is of 32-bit integer, the signed integer. You have another feature over here, that is the byte, that is 8-bit signed integer. You can have byte. The others are short int and long int. So we will see a first fixed size array, as we have already known about the fixed size array. So we will see 1 or 2 features or operations that can be done over here, which is unlikely not present in the Verilog incomplete. Here in what we all know, array is a collection of the variables, and usually they will be of the same type. And here you can have many operations with the arrays. Here, how do we represent a fixed size array is, we all know this is of the type integer. So integer type with the instance name given as low high, and we can give the range of the number of bits that can be there in this, that is 0 to 15. Either you can go with the regular default with the format that we use, or with the C style we can initialize it. And usually the Verilog stores all the element in 32-bit boundary, that is the long word. Now usually what we refer to, they are called as the unpacked array. That means you are going to refer to the dimensions declared after the object name. So after the object name, you are going to define the dimensions. So hence you can have dimensions of 1 in general, or you can have multi-dimensional unpacked arrays that are defined. So here as an example, we have taken here of the type bit, with an instance name being of unpacked, and the size of these. So this is a vector notation. So we are going to have 3 memory locations of 1 dimension here. So it is 3 here, and in that 3, that is your its name here as unpacked, but we for an reference sake it is taken as array to represent the array b underscore. So So since we have 3 here, indicates 0, 1, 2, and each array of each one is going to be of 8 bits. This is the regular representation that we have been using it in Verilog. So, but what is the drawback that we have noticed over here is that we cannot feel it as drawback, but what visualization we get is that when we go for this, since it is going to take a default of long word of 32 bits, so what happens here is that you are going to have spaces that are being unused. So to make it more compact and use all these unused features, we have what is called as packed arrays. So packed array, when it is usually the dimensions are declared before the object name. So if this is the object name bytes, it is the dimensions are mentioned before it. And if they are of one dimension, by default it is the vector notation that we use it in Verilog, vector width. So what are the things that can be used under packed arrays? So you can have bit, logic, the keyword, especially the data types that can be used for packed. Bit, logic, reg, wire, and the other net types can also be used. And you can also use it with other packed arrays and packed structures. So there is a limitation here. So can be limited, but shall not be at least 65536 bits. So now how is this being interpreted or read as? So now we, since it is packed array, the dimensions are mentioned over here. So you have two dimensional dimensions mentioned over here. So it is of the object name is byte. So when you say byte here, so 0 to 3 there are 4, and 0 to 7, that means it's 8 bits over here. So it is 4 into 8, that is 32 bits. So 32 bits is nothing but 4 bytes. So how it is allocated? So total is of 32 bits. So you have 0 to 3. So you have 4 bytes, 4 split up locations, and each one is of 8 bits. So you have 4 separations of 8 bits each. That is how it has been interpreted in packed. Now, this can also be a combination of packed and unpacked. That means you can have mixed packed unpacked array. So how can we interpret it as? How is it shown? Adding on to this one itself. So you have bit data type bit where the two dimensional mentioned priorly, so it is packed, and there is an dimension mentioned after the object name, hence it is an this becomes unpacked. So it is a mixed packed unpacked. Now how do we interpret it or read it as? So that is 3 locations of 32 bits each. So how the data will be filled in? So we have 0, 1, 2 arrays, and then you have 0 to 7. So this is, as I told you, the 32 bits. So you have 4 separate bytes with each one being of 8 bits. So that means you have 4 bytes separate mentioning. So if you want to access any individual one, any individual location, memory location in particular. So if this one has to be accessed, so so how are we going to mention that in our program if to particularly access, or if you want to change one bit out of this entire data set? So then we have this one will be represented as you are having in the 0th memory location here 0, and this is of this first dimension you take, it is this is 0, 1, 2, 3. So this will be of the 0, 1, and in the first one the location it takes is 6. So it is like 0, 1, 2, 3, 4, 5, 6, 7, right? So each one is of 8 bits. In that it is of the 6th one. So if you want to change this value, this is the way in which it is being written. And if you want to change the entire data set, that is the 8 bits all at once, then you can go for selecting the row in which it is, that is the memory, that is 0th one and the third set. So this will become the three-dimensional representation value for in particular axis. This will be accessing the entire bit range, that is the entire byte. So if you want to change the entire uh, row itself of 32 bits, then this is the way in which you can write. That is, you just have to give a B array, that's the name, and the exact one is of the second column, of the second row, that is 0, 1, 2. That belongs to 3. Along with that, so now we have discussed till here, they were all with respect to fixed arrays. Now, what we are going to see, the unique feature that is being allocated in System Verilog is the dynamicity in dynamic operations. So the dynamicity is introduced in 3 ways here. First one is dynamic arrays. So in dynamic array, what happens is, usually when you're going for fixed size, the size is usually set during the compile time itself. But now in dynamic array, so what happens is the allocation and resizing will be during the simulation, it will be allocated during the simulation. So that means it's usually done during the runtime. And then you are going to consume minimal amount of memory in comparison to fixed size array. Now, here how are we going to identify whether if it's a dynamic array? So the dynamic array is identified with the syntax which has an empty square block. Now, this, how do we initialize it? So int, there's a dynamic name given which has an empty space over here. So you have dyn and d2. So we have taken 2 arrays and they are kept empty. So that means initially we have not declared what is the size of the array. Then if you but still you have to have the memory allocated during runtime at least. So how many, what is the size, the entries that you need to do in that. So you have to allocate that space. So for the to allocate space, you have to use the keyword new followed by the square bracket. In the square bracket, you are going to write the size that has to be allocated, the space that needs to be allocated. So the 2 keywords that will complete or to make us identify it's of a dynamic array is this. So you will have, when you begin it, so it is, so dyn. So this is initially a dynamic array, nothing is mentioned, but when you're going to run it, you're going to allocate 5 elements. So you're going to write 5 here, allocate 5 array elements, and that has been allocated with the keyword new. So by doing this will help us passing the number of entries in the square bracket. It will help during the runtime to allocate the memory for it. Now, you can also have some other extra features for dynamic arrays, that you can have delete, you can know the size of the dynamic array. Like once the operations are done, you want to know the size in the end, then you have the keywords that can display the size. Along with that, now if you want to copy the data from a fixed array to a dynamic array, if during the operations you want to transfer the data from fixed array to dynamic, then yes, that can be done. You can also allocate a dynamic array to the fixed size arrays, but the only condition that will be they have to have the same number of elements. Since it is dynamic, so we may not be allocating the elements initially, but if you want to do the transfer of arrays from dynamic to fixed array, then you will need to have the same number of elements. So in the background, System Verilog itself does the operation of it. So this is one type of dynamic array. Then there is Another type of array operation that can be done, and that is called as the queues. So what will queue do? Mainly in the queues, what happens is you are doing an operation where you want to expand and decrease the size, or the growing and shrinking of the data size. You want to do it, but you don't want to affect the performance. So the performance will be good. So adding and removing of elements can be done anywhere during the operation. Then you have to go for an array, initializing the array as queues. So when we go for queues, it will be easy for operations like searching and sorting, which will be faster in comparison to the fixed size arrays. So this kind of feature can be identified by the keyword or by the symbol, the dollar symbol here. So the elements of the queue are numbered from 0 to dollars. So dollars itself indicates that you are talking about queues. The empty blocks will tell dynamic array. The square bracket with a dollar symbol will indicate it as queue. So now if you want to have to insert any values in between the queues, when the queue size is too long, then it might become a slightly tedious process. Until if we eliminate that condition, then the adding and removing of any elements and increase and decreasing the size of the queues is very easy in System Verilog. If in case the allocated size for the queue is less, then but during the operation the size of the queues is been growing. So then the System Verilog itself will automatically allocate the extra space that is required for the operations. So if there is an ambiguity in on using the size, allocating the locations for the operations, then queues is the best option. So as an example, we have taken over here indicating the value j as int is equal to as 1. Now here b, there are two queues, B and Q. So B having the value 3 and 4, and this Q having the initially it's of the size 0 to 5. Okay, so this is the initialization. Now we can have some operations done. As I told you, you can increase, add, remove and all that. So you can have many operations that are relevant to this queues. So I have taken only insert and delete over here. Apart from that, you can take push, pop, then you can even push and pop it either in the beginning or in the end. So based on the location, you can have these operations. So here you can see in this example, I have taken to insert. So insert a value into the queue. So taking the condition of queue here, that means once the operations are done, I am resizing the queue array. So queue insert. So taking the queue, and here 1 represents the location. It's not the value that you are going to insert, it is the location where you are going to insert. So then here j is what you are going to insert. So in the array size, if it's going to be 0, 1, 2. So this is the queue, right? So 0, 1, 2, the memory location I'm talking about, the positioning 0, 1, 2. So in the first location, insert the value of j. So j value is 1. So you will be inserting it as 0, 1, and then you'll have 2, 5. So insert 1 before 2 is nothing but the location. So the j value is 1. So hence 1 is inserted. Similarly, if I take the next example, now the queue is been updated to this these values, that is 0, 1, 2, 5. So in this it says for the third location insert the B values of the QB. So what we are going to do is that third location will be 0, 1, 0, 1, 2, 3. So at where 5 is there from the previous one, there it had you have to insert the array elements of B. So hence it is going to be 0, 1, 2, 3, 3, 4 is being inserted and then 5. So insert the whole Q. This is there, so you are inserting the Q there. Now at which location, that is being mentioned here. Now next one comes Q delete. I want to delete 1. So the delete the element 1 hash 1. So 0, 1. That is the operation of delete. So this is of the queues. Now again, if we want to move data from fixed to this one, can it be done? Yes, it can be done. Since the elements in the queues are stored continuously in the locations, so it will make us easy for adding, deleting and also push and pop elements. If you want to copy the content into the queue, yes, you can copy the content from the dynamic array or from the fixed array into the queues. You can do it. But once the size of the queues increases, then the timing will also linearly increase. The next operation here we have is the associative arrays. So in associative array, what happens is sometimes we are trying to use a dynamic array if you consider, if you take also, or if you take any modeling where you are modeling a processor which has some gigabit address ranges. But thing is that in the gigabit address ranges, all the locations may not be used. You are using a few of the locations, or I can say you are only going to use allocating only of the few. In that time, if you already fix it and keep the size of the array into some gigabit address ranges, so then what happens is you are simply we are simply wasting so many addresses, and we are booking it such that no others can use it. So what we can do is that when we know only a few of them are being used, why not allocate the memory only when you're writing into it? So that feature is given by associative arrays. So here how does this work? So it is going to store the entries in a sparse matrix. So what exactly is a sparse matrix? It's a matrix which has more number of zeros, unlike the number of values that has to be put in. So when these entries are stored in sparse matrix, so whenever you are going to write any element, any value into certain memory location, only then it will be allocated, else it will not be allocated. So that is called as the associative arrays. And how do we declare it? You are going to declare it with the value with the square bracket and the star into it. So you have logic 64 bits that is required over here, star, and you have an IDX as a variable which is set to value 1. So how are we going to initialize it? So since you are going to repeat 64, you repeat the things for 64 times. So repeat begin. So you are going to have the associative index given as IDX1 with the location 1. So then IDX you are going to assign the values. So this is just an initialization process, not a function that it is actually being doing. So this just to show where the associative arrays can be used. So this associative array, it will implement a lookup table of the elements of its declared type. Whichever type it is you are going to declare it, in that form it will create the lookup table. So the add-on feature, to sum up, the add-on feature here is that you don't have to allocate any storage for it until and unless it is being used. So these are the array methods that are available uniquely in System Verilog. So as I told you, these are all can be allocated only when they are necessary, and these features are not usually synthesizable. You cannot synthesize them. So fixed size arrays are only synthesizable, and the operations, anything that can be done on them, they are also synthesizable. Coming to the next important feature that is available here is randomization. Now, what exactly is a randomization? Here, the testing that we are trying to do, it need not be limited to the stimuli that we give in the order. So the testing has to be done in general for all the conditions. So you usually have the testing here casually done as a directed testing. So wherein you have the, or you will be aware of the results that you are going to know. That means it will find the bugs in the directed testing. It will find the bugs which can be predicted or will be known. So that is directed testing. But as the design has been more complex, so directed testing can lead us to such that we might miss out some of the conditions for testing. That can be overcome by what is called as randomization. So here you are going to generate random values to variable, and that is a constraint random test. So you are going to give the conditions for randomizing as well. So it's given as constrained random test. So that will find bugs one never would have thought of by using random stimulus. So the basic glitches that can occur due to the changes of the stimulus, which might be unlikely found when you're going for directed testing, because there you might tend to take up some sequential inputs, that is in the predefined way. There some of them bugs might have been missed, but when taking random, so the glitches can also be avoided. So that is the add-on feature here. When you go for randomization, how do we randomize it? That becomes the thing. So here Verilog, you had $random method for generally generating the random integrated values. In System Verilog, you have the keywords rand and randomize, that is going to help us in randomizing the thing. So what exactly with the keyword rand do? So if any variable is been declared with the keyword rand and are standard random variables, the values are uniformly distributed over their range. That means if I take this example, now rand bit 3 down to 0 for the address. So now here address here, if I take 3 down to 0, it will become 4 bits. So 0 to 15. So 16 bits, they will be distributed uniformly, and their ranges, and it will such that all the situations all the values from 0 to 15 will be tested. So and they will be selected randomly. But there is one more thing which is called as RAND-C, that is random cyclic. So if you use this term, what happens is the randomization, it will not repeat the random value until every possible value has been assigned. That means if we are taking the similar example here with the cyclic constraint, what happens is until and unless all the possible conditions are completed at least once, with the probability that it has done at least once, only then it will go to the next cycle of repetition. So it will not repeat the random values. So that is the feature that is available in RAND C. Now, the randomization is more effective in System Verilog because it is being using the concept of object-oriented programming. So the random stimulus generated in this is more useful when we are clubbing it with object-oriented. So the keyword that was required over here is to randomize. So here we will see one example how are we doing it. So here, this is the class over here. In this class, all the variables should be random and public. First of all, the variables should be public and random. So that is the first criteria. So here we have taken source, destination and data. They are random, 32 bits. And we have rand C, that is cyclic random for the kind. So that is of 8 bits. Now, so this will give us the maximum control over the device under test, stimulus and control. So mainly some of the test bench constructs that we see here will be covered in tomorrow's session. So these are the things, and there is some kind of limitation that can be done since we are going for constraint random testing. So we are going to assign some kind of constraints. That constraint has been assigned to the source. So limit the values of the source. So either greater than 10 and less than 15. So here is the constraint that we are assigning along with the randomization. Now here the randomize that is been written here. This randomize will assign the random values which is there from the class labeled as rand and randc, and it will see that all the constraints are been obeyed. So this is the one who is going to make this happen. Along with that, you want to see the results. So the assertions are there which will check and as well as print, and if there is an error or if there is any kind of failure or if there is any success. So that can be done with the help of the assertion. So you have written here as assert. So this is the main feature of randomizing. So this randomization can also even fail. There are chances that randomization fails. The chances where it fails is when the constraints that are given will create ambiguity. When the constraints are not clearly mentioned, the randomization fails. In general, we can say if the randomization succeeds, the function which is there, it will return 1, and if it fails, it will return 0. Then the next feature in System Verilog is of the ways in which we can create the threads. So unlikely in in Verilog, you have mainly fork join. Here you have 2 more. So this threads are the process, that's a piece of code that can be executed as separate entity. So generally in Verilog, you have begin end that has been used and fork and join. So begin end are used where the statements which are written inside them, they are being executed sequentially. But when we go to fork and join, the okay, so But when we go to use fork and join, what happens is when you go for this option, the processes or the statements which are written inside them, they are all executed parallelly. So that is the major difference having fork, join and begin and end. So begin, end usually sequential, and fork, join for uh, parallel executions. So here we can see here in this example, what will fork and join do? So there is a small change over here. It should not have been 15, it should have been 20. So how does it take? So the clock 0 after the time unit of 5. So you are going to fork it so such that A will take the value of 5 after 5 units, B will take the value of 0 of 10 units, and then you are going to join it and make the value of clock as 1. So this is being done parallelly. Okay, this has been done parallelly. So once, but as it is increased here, all the after the completion of all the child threads, only after the completion of child threads you can join. So the timing will be added over here in this case. So here if I take this example, this is just an example that shows a parent and child threads. So here when the fork is been called, so all the operations that are written inside them, they take place parallelly and are executed as separate. So this can also be visualized by an example here. If you can see here. So initially the statement 1 and 2 gets executed, and then it goes into fork join where you have 3 processes, they run parallelly. Once the process is complete, only then it goes to the execution of statement 3 and 4. So this is how fork join actually works. Moving to the next one. So in the next one which we have, that is the process which is uniquely present in System Verilog is fork join any block, and there is fork join none. So these are the features that is exclusively available in System Verilog. So what exactly happens over here? Fork join any. It will finish when any child thread gets over. So here there are 2 child threads. If any of them gets over, so this will change the value. So clock initially has 5, that is after 5 time units. Here A will be 0 and B will be 0 at 5 time units 5 and 10. So whichever gets completed first. As soon as that completes, join it and go for the next one, that is changing the value of the clock to 1. So taking this example, the A gets initially completes first. So hence clock will be 1 at time unit 10. So this is the way in which, so if this is its fork, the fork will fork the child processor separately. So any of that can be connected. So if we go for checking through an example, we can see over here. So statement 1 and 2 gets executed. Once it's been forked, all the processes will be done parallelly, but process 2 gets completed earlier. Hence statement 3 immediately takes off the process 2 and then executes 3 and then go for 4. So the statement 3 doesn't wait for the completion of process 1 and process 3. Unlikely in your in fork and join, the statement 3 would wait until all the processes are complete. Only then it would go for joining it and then go for the execution of statement 3. That was in join and fork and join. This is fork join any. Then comes fork join none block. So what happens in fork join none? Here finishes as soon after child threads are spawned. That means you are going to fork it, but as soon as you are going to fork it, you are not going to wait for any of the child threads to complete its process. You are not going to wait for it. You are just going to go for the next execution of the statement which is beyond it. So here what happens is at 5 your after clock is 0. After 5 time units, you are going to fork it. So when you're going to fork it, after 5 units, you have A as 0. After 10, you're making it B as 0. So here, join none. So this particular operation doesn't wait for any of these to take place and directly go to make the clock value as 1. So hence the T is 5 because clock 0 after 5 time units, immediately make it as clock 1. So this is independent of the processes that are taking place inside the fork once been forked. So here the pictorial representation you can see here. So they are all separate and they have all separate endings. So they are not going to be dependent. The join will not be dependent on the completion of these child processes. So you can see that through an example in this form. So here you can see we have statement 1 and 2 executed sequentially, and once the completion of 2, once it's been forked, the process 1 and the statements are they all begin at the same time. So statement 3 and 4 are not going to wait for none of the processes to be completed. So yeah, to come up to all these, to sum up in the end, we have gone through the basics, essential knowledge of System Verilog. That is, we have covered its extraordinary features. Then we have seen the unique array features that are available in System Verilog. And each of these arrays that we have discussed will have many other intermediate operations that can be done on them, which will be in depth, but as of now we have not discussed them. Apart from that, we have discussed some other unique features, that is the randomization that is available for verification of the design, wherein we have which has been possible with the concept of object oriented programming that we have, which will make the randomization more effective. Then we have seen another the interprocess communication for the threads. We have seen we have fork and join. So begin and end was sequential that we have already used in Verilog. Fork and join is also there in Verilog also. But in System Verilog, you have fork join any and fork join none as an add-on feature. So this is the certain set of basics that we have covered. So these are the resources that have been referred to come up with this presentation.
Yeah, thank you, madam. Let us see if we have questions.
Yes, sure, sir.
I think there is a question from Ms. Durga Devi. I may unmute her so that she can ask her question.
Yes. Hello, madam.
Yes, ma'am.
What about the other versions of this Verilog, madam? System Verilog. You were talking about this 2001 version. Is there any new version available, madam? Why still
And
we
I
are
have,
using this? Yes.
yes, ma'am. Like a new version as such is not there, but as they are moving towards this UVM, so there is the thing. Actually, a system, it's been moved towards UVM now. That unification methodology manual is there for us to know the industry level verification process.
Okay.
So this is just the entry level. That is when this has been over, what to say? This is just a basic level which will help us to understand the verification, industry level verification operations.
Okay.
That is
Ma'am,
why it's still in the thing.
Okay, ma'am. I have another question, ma'am.
Yes, ma'am.
You explained about that fork join that
Uh-huh.
steps. In that,
Yeah.
statement 3 and 4 executed without considering that fork and none. That statement. Is it right?
For which one you're telling, ma'am?
The last one you explained, madam. Fork and join
For
none.
join none. Yes.
Process 1, 2, 3 executed. After that, simultaneously it executes that statement 3 and 4, no?
3 and 4, yes.
Yes. But that time it doesn't consider about this fork and none instruction. Is it okay or?
No, it actually this particular feature will not consider the processes that are there inside.
Okay.
So they are going to be independent. They will be independent of whatever is there.
It doesn't depend on that none instruction, isn't it?
Yes, sir. Yes, ma'am. It doesn't depend on them.
Okay, ma'am. Yes. Thank you, ma'am. That's
Yes,
all my
thank
question. Thank you.
Yes, thank you.
The first question, myself is Shashidhara. The first question, which is what are all the issues in the scalability for formal verification? So I think I will cover in tomorrow's sessions for that issues. So we have a number of issues which can be derived to different levels actually. If I take simple SOC which is presented earlier with CPU, there is so many processing element issues which can be considered, design issues can be considered. So I think tomorrow I will discuss more about that issues, formal model issues. I am unable to check out the chat box here. If anybody can.
Yeah, chat box is like right side.
Yeah, got it. So only one question: what are the scalability issues of formal verification? Vineet, any other questions are there, Vineet? Which verification method is suitable for SOC?
We don't see any other questions possibly.
There is one more, sir. How OOPS interfaced with the System Verilog?
Okay. How OOPS is interfaced with System Verilog? In System Verilog, we have also classes. We have can be inheritance. We can be made it inheritance. So we can have polymorphism also. So can be called. So some of the OOPS concepts is inbuilt. Some of the OOPS concepts can be derived over there. Like as Shruti is while explaining, she taken fork join any. Fork join any is one of the concept of OOPS concept. So it can be derived to test the multiple factors. So if you are testing any ABP buses, so the multiple properties arrangements can be made and made it to testability. So you can derive each property as a class and you can cover, you can do the analysis. Let us say I want to do a code coverage analysis of the conditional statement of the switch statement. I will create two classes and I will go for a testing. So that is the one parameter which will be with the OOPS concept. Some of the issues which can be derived to the OOPS concept from the to the System Verilog, because System Verilog is developed based on the OOPS concept only. So the derivativity will be there with respect to that. We have two more HDL, which is with the Python, PyMTML and MyHDL. You can write the Python code and you can derive to an Verilog directly. So it can be a synthesized model. You can directly go for synthesis. So that we have. So no need of going with the C language there. So you write the Python code. So convert it to an Verilog directly with the MyHDL or my PyMTL. So and do the hardware modeling over there. So that is possible. Which verification method is suitable for SOC in terms of less time consumption? So that depends on, we can't say that. So which one is which verification method is less time consumption? So normally where you want the verification with respect to that, you can see that a suitability. Less time consumptions, we can't say which one is less time consumption. So but there can be that which design, which how much complex your design. So with respect to that, you can define the verification methods. So let us say I done one with a biometric, integrated biometric. So I designed the SOC and I written a verification methodology. So there I took two constraints. One is an feature values. The second one is an the speed of memory of storing. So I'm not looking at the speed. If I'm looking on the speed, the methodology itself will be changes. Looks on only the method where and all the time constraints so can be considered over there. So I looked only on the features and on a memory constraints. So that's why so those factors will not be will not touch to the timed values. So with respect to that, what are all the parameters or how complex your design, what you looks for, with respect to that, you can define your verification methodology and go further. So less time consumption we can't define over there in terms of that. Thank you.
There is, I think, a older question possibly in your talk. This is from Devendra Pal Singh.
Yeah, that I addressed, sir. That I addressed. What are the
scalability issues in formal verification?
Yeah, I addressed it, sir. First I addressed that, then I gone for this. Thank you.
Okay.
Sir,
Thank
sir,
you.
for
Thank you.
there is one more here. For System Verilog implementation, same FPGA kit is required or not?
System Verilog is a verification language. We don't think it with an FPGA kit. The targeted device may not be required.
Right.
So the derivative, if it's with an System Verilog or a Verilog or any other HDL. So if you have a bit file, you can directly dump to the FPGA kit. So no need of thinking on which language you are going with. So you are directly, if you are derivative or from the HDL to a dot bit file or dot some other file, so which can be adaptable to the FPGA, you can directly dump it. No need of thinking on the Verilog or System Verilog. Particularly, the System Verilog is an verification language than going with a design language. So usually we use an Verilog as a design language and System Verilog as a verification language. We didn't derive that System Verilog to the targeted device. So the Verilog can be derived to the target device, but any language, so it can be, if it can be derived to the .bit file, so which can be dumped. No need of thinking which language using and which FPGA using. So both are independent to each other for those purposes. Thank you.
To add on to sir, the only condition will come here is that not all System Verilog constructs are synthesizable. So that will cause a problem over here. So in Cadence also you can try, if not for FPGA, you can Cadence also, this will support. But again, synthesizable constructs has to be analyzed. If we are considering Xilinx Vivado, Xilinx Vivado doesn't provide an option for System Verilog selection of language. So in that case, that would be a limitation again, if we are talking about exclusive FPGA kit.
Any other questions are there, Shruti?
No, sir, none that I can see.
Vineet? Vineet, can we wind up?
Yeah, if there are no questions, I think
We're done for today.
Prashanti, you see any questions there?
No, sir.
So I think it's our duty to thank Professor Shashidhara and Ms. Shruti for engaging us for a long time and for such a nice talks.
Excuse me, sir.
Thank you very much, Professor Shashidhara and Ms. Shruti. Thank you very much.
Excuse me.
Yes, thank
Thank you. Thank you.
Hello. Sir, tomorrow
Yeah.
will be the lab section for us for this Verilog.
Yeah. I think Shruti will take care of through an EDA tool to demonstrate some of the programs.
So for that, what we have to do, sir? Like previously, what
Now
are the
we'll
tools
give
we
the
have to have in our
EDA
system?
tool address. No need. We'll give online. If you are connected to the internet, we'll directly do with an EDA tool. No problem.
Okay.
Yeah, if you have
No need
some,
of any.
if you have some,
No need of.
yeah, Professor, if you have some one-page kind of directions, what people can do, so they will be ready with that part. Kindly share it.
Yeah, I will share it. Yeah, I will share to you, sir. No problem. I will
Thank
share
you.
to you.
Yeah, thank you.
Today evening I will share.
Sure.
Thank
Thank you very much. Thank you.
Thank you.
So participants, thank you very much for being here. We'll meet tomorrow morning again at 9:45. Thank you very much.
Thank you, sir.
Thank you, sir.
Yes.